happy to have Professor Yan Liu at Beiyang University in Beijing. And today he's going to talk about quantum chaos in topologically massive gravity. Okay, thank you.
Okay, thank you very much for the introduction. So good morning, everyone. I hope everyone is healthy. I'd like to thank the organizers for the invitation. Today, I'm going to talk about quantum chaos in a two-dimensional rotating fluid, which is due to a rotating BTZ black hole in three-dimensional topologically massive gravity. This is based on my recent work in collaboration with my postdoc, Avinash Raj. Let me start from some basic knowledge about chaos. So as we know from classical mechanics, for a non-integrable system, the system will be exponential sensitive to the initial conditions. This is known as butterfly effect. More precisely, if we change the initial condition of the system by a small value epsilon, then the system will evolve by a difference epsilon times to e to lambda t. So this lambda is known as butterfly Lyapunov exponent. This lambda is known as Lyapunov exponent. In general, for system, if the phase space is of dimension 2n, then we will have 2n independent Lyapunov exponents, and we will focus on the largest one. As the system evolves further, and at long time, there's a typical behavior, namely mixing. That is, for example, this is the phase space of the system. And if we pick up any two regions, that is the open set of the phase space. For example, we choose this blue regime and any other regime. And for example, this one. So the system evolves and eventually so we say the system will overlaps with the other given regime at an arbitrary accuracy. So this is the mixing. During the period of mixing, the system will completely forget about the initial condition. So we say this mixing is very crucial for summarization. I should emphasize that both exponential sensitivity to initial condition and long-time mixing are two necessary and important conditions for system to be chaotic. It's not enough to only have one of them. And at very late time, the system will evolve back to the initial state at an arbitrary accuracy. This is due to the Penka recurrence theorem. And the time scale for this Penka recurrence is at order of e to power s, with s the entropy of the system, which is typically much larger than the age of our universe. Okay, these are the properties of classical chaos. In classical chaos, the dynamics is still deterministic, while chaos is about the sensitivity of the system to the initial conditions. On the other hand, we know in quantum mechanics, there is an intrinsic uncertainty. Therefore, the classical coarse-graining should be set by h bar. And the picture above about this classical chaos should be modified after a certain time scale, namely the Ehrenfest time scale. The Ehrenfest time scale is defined as follows. So it's so here lambda is a Lyapunov exponent, and this integration is the minimal area in the phase space and h bar. So after this Ehrenfest time scale, for example, so this Penka recurrence time scale is much larger than this time scale, and it should be modified. So then it's natural to ask what happens for classical chaos at non-zero h bar. So that's the question of quantum chaos. And we have also a question, for example, if we set h bar to be 0 in quantum chaos, is there any correspondence between quantum chaos and classical chaos? Is there any chaos behavior for solutions of quantum systems, and so on? Those are the basic questions in quantum chaos. There are several different approaches to study quantum chaos. The first one is known as late time chaos or spectrum chaos. The idea is to look at the energy spectrum of the system and study the distribution of the energy level spacing in the system. It turns out for integrable system and the distribution of the energy level spacing based the Boson statistics, which is the dashed line. This is for the integrable system. And for chaotic system, the distribution of energy level spacing based the Wigner-Dyson statistics, which match perfectly with the random matrix theory. That's this solid line. So for a system, for a large n system, typically the energy level spacing is of order e to minus s with s the entropy. And so the time scale for this distribution should be of order e to power s. So this is the physics happened at of order Penka recurrence time. So this is the late time chaos. On the other hand, we know in classical chaos, there is anytime exponential sensitivity to the initial condition. So what's the quantum generalization of that exponential behavior? So we can start from some semi-classical intuition. So the idea is to look at, for example, this dynamical equation. We can say that this Boson bracket should go like exponential function as a function of time. And we quantize it, replacing this Boson bracket by the Dirac commutator, and then the expectation value of this commutator square should go to e to power t. And here we can generalize it to be arbitrary operators at different time. Well, generalize this canonical momentum and canonical coordinate to arbitrary operators. So we can look at this commutator square expectation value. So this expectation value.
Excuse me, Jan. Before moving further, I have one question. So you already explained, but I just missed. So in the first case, in the statistic, in the Wigner and Poisson distribution, you said it is about the large time characteristic thing. In what sense it's large time? If it's just a level, energy level, then it's a time independent property.
No, it's not a time dependent. So I'm just arguing that for a large n system, so for a large n system, I mean the many-body system, the spacing is typically of order e to power minus s with s entropy. So the uncertainty, like the uncertainty of time, should be of order e to power s. So that's the time scale of this property. I think there's another characteristic of the late time chaos is called spectrum form factor. So the spectrum form factor as the function of time, we can say that the late time there's a universal plateau and there's one plateau. I think you know much better than me. And that time scale should be of order this e to s. It's very late time. It's very large time. So this is we need late time.
Okay.
And this is any time because for you know much better. Yeah. So it's like a square time should be much larger, much smaller than this time scale.
Okay. Thank you.
Yeah.
May I ask a question?
Sure.
Yeah. So in the previous slide, you have some definition of the eigenfest time. and it's an integral over phase space. I just missed what is this sigma?
So sigma is some. So this is just I mean, this is not I don't take it as a very strict definition. So I mean, it's just a kind of argument. So this we look at so H bar is the minimal Cosgrini. It's like this kind of picture, minimal Cosgrini, and the uncertainty is set by H bar. And so at time scale, some H bar times e to lambda t is very, very large, like of order 1. So we can see a time scale. And so this this integration should be some area in the phase space.
Okay.
So yeah, it's just some argument about the minimal areas in the phase space.
Ah, I see. So thank you.
Yeah, that's fine. So now, so we have argued that in an intuitive generalization of this exponential growth in classical chaos to quantum case is look at this expectation value of this commutator square. So here beta is the inverse temperature and WV are two very generic operators in a quantum many-body system which take values at different time and different space. So we can look at this this expectation value. So at any time, say t equal to t1, and t1 is small, so we say that this is WT1 x1, for example, and this V naught, V0. So there's no overlap between these two operators. And then the expectation value should be very small of order 0. And at late time, I mean at a large time, so t equal to 2, for example, there's some overlaps between these operators. Then we can say it should be of order 1. So for chaotic system, we are expecting that there's a exponential growth during this period T1 to T2. So this exponential growth in this C function should be a signature of quantum chaos. And let's have a further look at this commutator square. So it can be interpreted as a probe of the sensitivity of a system to the initial conditions. It can be seen in the following way. We can expand this commutator square as two functions, C1 and C2, and write it as the norm between different states. And we see actually it contains two kinds of norms. The first kind of norm is the norm between the same state, and the second norm is the norm between two different states. So we see that C1 is of order 1 during the involution, but C2, I mean, due to the exponential growth, so there's a exponential growth in C2. So C2, this commutator square, this norm between two different states, or its auto time order coordinator, this C2 is the K probe for this exponential behavior in C. Okay, and so C2, because it's a norm between two states, and these two states are prepared at slight differences at the initial. This is a little different initial condition. So it probes the sensitivity of the system to the initial conditions. For interacting quantum many-body system, the C2 behaves like this one. So it has an exponential growth, and this exponential growth depends on T and X. So here lambda is the quantum generalization of Lyapunov exponent, And VB is the butterfly velocity. I should emphasize that this exponential growth or decrease should be within this time window. So here, T star is the Scramble time, which means this term becomes very, is of order 1, this time scale. And this term becomes significant. And this time scale is any time scale, is a thermal time scale, summarization time scale. For example, for strongly interacting system, Nagian system is of order 1/T. So for different chaotic systems, the time dependence are always the same, but the spatial dependence could be different. So so for example, in many non-maximally chaotic systems, there are some diffusive spreading of this spatial dependence. Both Lyapunov exponent and butterfly velocities are important parameters for quantum chaos. That's the two important parameters we shall focus on. In holography, we can compute OTOC from the dictionary, and this was proposed by Sinker and Stanford. So on the gravity side, it turns out OTOC can be computed from the amplitudes for 2-to-2 scattering of particles due to 2 operators in a black hole geometry. And in certain limit, the dominant contribution is related to the gravitational shockwave calculation. And it was found that for gravitational system, we have a very universal Lyapunov exponent. It's 2 pi t. But the butterfly velocity depends on the details of the black hole geometry. For example, the chemical potential of the system, or the if it's gaining of the system, and so on. There is a very interesting bound on the chaotic parameter. So it was discovered by Marcina, Sinker, and Stanford. They started from this coordinator, and they found that for systems with typically large n system with a large hierarchy between summarization timescale and Scramble timescale. So analyticity in this coordination function demands that the Lyapunov exponent has an upper limit, so set by 2 pi t. This holds for very generic quantum many-body system. And for black holes, for the strongly interacting system due to black hole, so they saturate this bound. This system is namely as a maximally chaotic system. Actually, this is the main driving force behind the SYK and JT gravity duality. So up to now, I have talked about quantum chaos from the perspectives of OTOC. The Scramble in OTOC are the important probe for quantum chaos at any time. So surprisingly, there's another probe for quantum chaos, namely pole-scapping. Actually, this has been talked by Konrad Ham this Monday, and will be talked this afternoon, which I really very looking forward to. So naively, hydro and chaos are totally different, because chaos is about, so hydro is about the non-time behavior. But it was found first holographically by these people, and then from the effective theory of hydro, they found that actually there are deep connection between hydro and chaos. It's from the pole-scapping. That is, if we look at the energy density coordinator, the retardative coordinator, there exists a special point, namely omega star and k star. At this special point, the retardative Lagrange function has this property. Its denominator and numerator are both of them are 0. So it's 0 over 0. It's an undetermined function. And this special point, so it's a pole and the residue is 0. So it's called pole escaping point. This pole escaping point is related to the Lyapunov exponent and butterfly velocity in this way. There are lots of examples of pole escaping, like SYK model and black hole solutions. Pole escaping also exists for the 2-point coordinator of other operators. However, only the one, the sound mode or the energy density coordinator are related to the chaotic parameter. They're pure imaginary and has this kind of relation. So we have seen that the scrambling behavior in OTOC and the pole escaping are two important signatures for quantum chaos. So the motivation of our work is to study the connection between these two different signatures, especially for systems with multiple Lyapunov exponents and the systems that is not maximally chaotic. We will study the rotation system and from holography and include the massive graviton on the gravity side to study this kind of system. Our strategy is to study 3-dimensional gravity because it's much simpler and we can do lots of calculation from the dual CFT side. So in the following, I will first talk about the quantum chaos in 3-dimensional Einstein gravity. Then I will talk about the quantum chaos in 3-dimensional topologically massive gravity. So now let's first look at 3-dimensional Einstein gravity. So this is the action for Einstein gravity. And in 3 dimensions, we know there's no local degree freedom for the gravitons. So what the solution of Einstein equation is locally ADS3. Nevertheless, there's a famous black hole solution, namely the BTZ black hole solution. So this is the metric for BTZ black hole solution. And the FR is the in-blackening factor and takes this form. TR, phi are the coordinates. So this black hole is characterized by R plus, R minus, which are the inner horizon and outer horizon of the system. And the dual thermodynamic quantities like mass, temperature, and angular velocity or angular momentum are completely determined by R plus and R minus. So the dual theory, the 3-dimensional Einstein gravity on this black hole, BJ black hole, is expected to be a CFT, which is factorizable. That is the left moving CFT and right moving CFT with different temperature, but the same central charge. So here, this angular direction is periodic. So phi is periodic. Nevertheless, at high temperature, which means beta is very small, or L is very large. In this limit, we can take a specific limit. So we can take a so-called decommodification limit. That is to view this phi as a non-compact. So this is actually a boosted Brun solution. Actually, there are lots of evidence for this limit. So for example, in this limit, the dual theory is supposed to be defined on a cylinder. There are lots of evidence for this correspondence in this limit. For example, the 2-point coordinator, the entangled entropy, and so on. And we shall focus both on this periodic condition and this limit. The OTOC for 3-dimensional Einstein gravity has been computed clearly by Kuyan Kim and his collaborations in this paper. So they obtained this result. The OTOC is a function of t and phi in this form, and it contains 2 exponential terms. These 2 exponential terms, the coefficients in front of the 2 exponential form is very small. It's a small quantity, And this exponential form has beta plus, beta minus dependence. Beta plus and beta minus is the inverse temperature for left moving CFT and right moving CFT. So naively, we have two independent Lyapunov exponents from this calculation, which are lambda plus minus, and the corresponding butterfly velocities are the speed of light. So let's look at the butterfly. Let's look at the Lyapunov exponent. And with this lambda plus, we choose minus here. With lambda minus, we choose plus here. This is just for convenience. So we see that the Kills bound, which is 2 pi t, is within the window lambda minus and lambda plus. So it seems that the Kills bound is violated. There's an argument suggested by QMQI and his collaborators. So we can view the dual CFT as a product of left moving CFT and right moving CFT with different temperatures. So for each CFT, the Kills bound is actually saturated. There's no problem at all. If we are more careful, actually there's a subtlety here. So in this computation, we first take the so-called decommodification limit. If we take and then do the computation, and on the other hand, if we first if we first do the computation and then take the decommodification limit, we see what happens. So this was done by Mark Mason and Sarosi in this paper. If we consider the angular coordinate is periodic, so phi is periodic. Actually, this h should be a periodic function. And if we consider this fact, this will put a non-trivial constraint between the coefficients C1 and C2. Actually, there is only one independent constant here. So the final form of this OTOC should take this kind of form. And with this coefficient are totally determined by the black hole geometry data. For example, the angular velocity, this is a company determined coefficient, and it's a sum of two exponential functions. So if we consider the fact that the angular coordinate is periodic, this OTOC doesn't have a simple exponential dependence on t or phi anymore. Nevertheless, we can, for example, for any fixed phi, for each fixed phi, we can look at some limits. We just fix some phi and take it as a function of exponential function of t. For example, we fix this phi to be 0, so we can formally define this sum as a function of e to some effective instantaneous Lyapunov exponent times to t. And we choose this phi to be 0. Actually, it can be chosen arbitrary. And because phi is periodic, it's just a shift of this instantaneous Lyapunov exponent that will not quantitatively change the story. So this instantaneous Lyapunov exponent will depend on t. So this is one example. If we choose the angular velocity of the system to be some value and the system is periodic, so this instantaneous Lyapunov exponent as a function of t is as follows. It's a periodic function first, and second, at different temperatures, it has different profiles. For example, this from this blue, red line, green line, orange line, and blue line, the temperature is increasing. We increase temperature from 0 to infinity. So at high temperature, this infinite temperature, the instantaneous Lyapunov exponent behaves as this blue line is a step function, and it takes values between lambda minus, this is lambda minus here, lambda plus here. So we see that the decompactation from the point of view of this instantaneous Lyapunov exponent, the the decommodification limit is commute with the calculation, which means if we first take the decommodification limit to the computation, we get two Lyapunov exponents. And the second way is that we first do the calculation and then take the decommodification, that is the high temperature limit. We also get this number plus minus. Interestingly, the average of this instantaneous Lyapunov exponent is 2 pi over beta, which saturates the chaos bound. Okay, so up to now we have talked about the scrambling behavior in three-dimensional Einstein gravity from OTOC. As we know, there's another way to study quantum chaos, that is from post-gaping. So now we will talk about the post-gaping in three-dimensional Einstein gravity. We will work in the decommodification limit. That is, we will use the angular coordinate to be non-compact. So the post-gaping can be obtained in 3 different ways. The first way to obtain the post-gaping is just from holography. So we know that post-gaping is a property of the retarded Lagrange function. To compute the retarded Lagrange function, we need to impose some boundary condition near the horizon. We see that if the near horizon boundary condition has some subtleties, we are modified the property of the retarded Lagrange function. And the first way is just from the near horizon dynamics. So if we expand the fluctuation near the horizon and look at the near horizon equation, we can see a degeneracy near the horizon. So at some point, this special point, so the constraint equation will be no constraint anymore. The coefficients are 0, so there will be no constraint on this fields anymore. So therefore, near the horizon, it seems that we have more boundary conditions, more acceptable boundary conditions, which makes the retarded Lagrange function undetermined. That's the basic idea. So we just follow this strategy, and we found that. So in this decommodification limit, because we just assume that this angular coordinate is non-compact. And in this limit, we found that at this special point, the coefficients, the near horizon equation motion becomes degenerate. So this is the post-gaping point. From the relation between the post-gaping point and the Lyapunov exponent butterfly velocity, we can get the Lyapunov exponent and butterfly velocity, which are exactly the same results as the one we obtained before in the decommodification limit from OTOC. And there's another way to compute the post-gaping. It just compute the Lagrange function, and from the Lagrange function, we read the post-gaping point, and this matches with the previous calculation. And there is also another, the third way to compute post-gaping is from field theory. So we can compute the retarded Lagrange function for CFT for the energy momentum tensor on a cylinder, because we are working in the decommodification limit. That is, the CFT is defined on S1 cos R. So we can compute the Lagrange function and study the post-gaping from this Lagrange function. We found that the post-gaping point is also contains this kind of post-gaping point. Therefore, the previous calculations on
Hello? Seems the connection is not so good now. Jan? You need to turn on your mic, Jan. You are now unmuted. Yeah. Jan, please unmute. Oh, yes, good. Yeah, good. Very good. Very good.
Sorry, the internet is unstable and I was just lost.
It's okay.
It's okay now, right?
Yeah, it's very good.
So,
Yes.
So,
Yeah.
so I think I have talked about this post-gaping from CFT method, and we
Yes.
get the same post-gaping point from CFT method. And I should emphasize that the CFT calculation doesn't depend on the details of the CFT. It works for chaotic CFT and also works for non-chaotic CFT. So this post-gaping seems to be a necessary condition for post-gaping, but it's not a sufficient condition for post-gaping. So, okay. Up to now, I have talked about the quantum chaos in three-dimensional Einstein gravity from both OTOC method and the post-gaping method. And in the high temperature limit or decompactification limit, we see the matching between these two methods. Now let's move to TMG case. The topologically massive gravity is a gravitational Chern-Simons deformation to Einstein gravity. This was first proposed by these three gentlemen, and it's very similar to gauge Chern-Simons theory. So here is the Einstein's action, and we have a deformation. This 1 over mu is a coefficient. This mu is related to the mass of the massive graviton in the system. And we have a specific Chern-Simons term which looks break the diffeomorphism, but actually the equation motion or the variation is a boundary term. The equation motion still preserves diffeomorphism. So any solution of Einstein gravity is still a solution of TMG. Therefore, the previous rotating BDZ black hole solution is still a solution of TMG. And now the thermodynamic quantities should be modified. It depends on the mu, and it has this form. Similar to the previous Einstein gravity case, the angular direction is periodic, and in high temperature, we can do a decompactification limit to view the angular direction as non-compact. The dual theory for TMG on this rotating BDZ black hole is left moving CFT and right moving CFT with different temperature, but also with different central charges. This is different from Einstein gravity case. Moreover, so we see this mu is the coefficient here because we have an epsilon tensor, and mu plus and mu minus is just a different definition of epsilon tensor, and we can focus on the positive mu case. And for mu smaller than 1, we see that the central charge, the left moving central charge is negative. Actually, it can also be seen that the energy, the mass of the black hole, the energy of the black hole can be negative in this window if mu is smaller than 1, because G, there's some constraint between M and G. We can see for some G, it's possible that the mass or the energy of the black hole can be negative. Actually, this has been discussed a long time ago. There might be some black hole instability within this window, within this regime. There also exists a special point, so-called chiral point. At this special point, the massive graviton become massless. So it's a theory without any massive graviton, with only massless graviton. So with massless graviton, it's subtle because Einstein gravity, we know it contains massless graviton, but it's diffeomorphismly trivial. So the extra massless graviton sometimes it can be trivial depending on the boundary condition, but there could be a new solution, so-called logarithmic graviton. So this is a special point, and they even argue that the theory is only well defined at this special point. Because mu smaller than 1, the negative central charge for CFT, mu is bigger than 1, there might be some negative energy for the massive graviton and so on. So we can also compute the chaos for TMG. The first way is from OTOC. And the result is quite simple. It's just a straightforward computation, and it contains 3 terms. These 3 exponential terms, which are related to Mason's gravitons. The first 2 are the same as the Einstein gravity case, and the third one is mu, is related to massive graviton. It's the function of mu, and we can say if we set mu go to infinity, that is the mass of the massive graviton is infinity, and the massive graviton can be decoupled from the theory. So in this limit, mu go to infinity, actually this term is not there anymore. We can reduce to previous results we can reduce to the previous results in 3-dimensional Einstein gravity. So for generic mu, and mu is not equal to 1, there are these 3 solutions. When mu equal to 1, it's also a special point. Mu equal to 1, actually this term is the same as this term. So there will be a new solution actually when mu equal to 1. So we will focus on the mu is not equal to 1 and the finite mu case. So we have an additional mode here. And naively, we have 3 Lyapunov exponents. These 3 Lyapunov exponents, the first 2 are the same as the previous Einstein gravity case, lambda plus minus. The third one is mu. We call it lambda m. So it's this from this is this form. It seems that it's the system non-maximum chaos. So now the story is different from the previous Einstein gravity. In Einstein gravity case, we see that the chaos bound can be argued that the natural safety and random safety with different temperature, but we can't do so in TMG case. So the corresponding butterfly velocities are here. So there's a problem here. There seems a problem here. So let's be more strictly to first do the calculation and then do the decomposition to see what happens. So we include the fact that the angular direction is periodic, and after include this fact, there is a non-trivial constraint among these 3 coefficients. And at the end of the day, we only have 2 independent coefficients here. And H1 and H2 are functions of this exponent, which I haven't written out here. So we have 2 independent instantaneous Lyapunov exponents in TMG. And for example, for phi equal to 0, we can define 2 independent instantaneous Lyapunov exponent. So we can compute the instantaneous Lyapunov exponent and work in the high temperature limit. That is the decomposition limit. We see that similar to Einstein gravity case, the instantaneous Lyapunov exponent behaves as step functions. These step functions are for lambda for the first instantaneous. So it depends on mu. If mu is larger than 1 or smaller than 1, their behavior are different. So if mu is bigger than 1, so this instantaneous Lyapunov exponents are steps function of between lambda minus and lambda plus. The second one is between lambda minus and lambda plus. So we see the results from decommodification limit. I mean, this result. So this is done by first taking decommodification limit, and we say we can reproduce them by first do computation and then take the decommodification limit. We can produce all of them. And the average of Lyapunov exponent is 2 pi over beta. It saturates the BF bound. There's a subtlety here. So this was done for high temperature limit. Actually, one can check numerically if we lower temperature up to of order, for example, of order omega, the angular velocity. If we lower the temperature further at some window, at some temperature regime, the step function is still well behaved. And if we take the limit at low temperature, if we look at the behavior of them at lower temperature, as we said, because the exponential growth only be valid in the time scale 1/t to the scrambling time. So the lower temperature, at lower temperature, if the temperature is too low, that the 1/t is, for example, is of order this one. So this exponential growth is not traceable. And the exponential growth is only works in this regime. Then we see the instantaneous Lyapunov exponent has the expectation value at lambda plus instead of beta 2 pi over beta. It might violate the chaos bound. That's for lower temperature. Okay, now let's look at the case mu is smaller than 1 in the decommodification limit. And again, we can see some step functions behavior, but in this case, we see that this computation seems not commute with the decommodification limit. So that is, if we take a calculation, if we do the calculation and then take the computation in some regime, for example, this regime, we only produce two Lyapunov exponent, well, but not all of them. We only produce lambda minus, lambda m, lambda plus, lambda minus is not here. And moreover, in a certain regime, for example, this mu is smaller than angular velocity, we see that the expectation value for this instantaneous Lyapunov exponent could be larger than 2 pi over beta. So if we take the expectation value of instantaneous should obey, this should satisfy the chaos bound, then this region is not allowed. Okay, this is the high temperature limit for instantaneous Lyapunov exponent. And we can also look at this function and do another limit. So this is a high temperature limit and also this limit. And we can see the both temperature dependence and phi dependence. Actually, we can produce the Lyapunov exponent and also the butterfly velocities. Again, in this mu smaller than 1 case, we can see the violation of Lyapunov chaos bound, and we can see the Lyapunov, the butterfly velocity could be much larger than the speed of light. So this regime seems unphysical. So from this calculation, if we impose that the chaos bound should be satisfied for the average of Lyapunov exponents. So we should, the physical allowed regime is mu is larger than 1. When mu equal to 1, the profile for the shock wave should be modified. This is the result. And we can do the calculation again by imposing this phi is periodic and compute the instantaneous Lyapunov exponent. We see that we can obtain lambda minus, which satisfies the chaos bound. So let me briefly summarize what we found from OTOC for TMG. We have found that in the decommodification limit, if we impose the chaos bound on the average of instantaneous Lyapunov exponent, mu is larger than 1 or equal to 1, is allowed. If we further lower the temperature and impose the chaos bound, these are only numerical evidence. If we lower the temperature, actually mu larger than 1 is not allowed, and only the chiral point is allowed. In the decommodification limit, if we impose the chaos bound on Lyapunov exponent, while not the instantaneous Lyapunov exponent. We see that mu is bigger than 1 or equal to 1 is allowed. That's from OTOC. On the other hand, there's another approach to study chaos, that is post-gaping. Same as the Einstein gravity case, we can study the post-gaping from different methods in TMG. First, from near horizon dynamics, we found the post-gaping points. There are 3 post-gaping points, which gives us 3 different Lyapunov exponents in the decompactation limit. We can also compute the post-gaping from holographic retarded Green's function. And for the Masonist graviton, or for energy momentum tensor, that's the same as the previous one. But for the massive graviton, which is also due to the fluctuation of the metric field with different fall-offs. And we found that the retarded Green's function for the operators due to the massive graviton have zeros, have post-gapings at special, this is a numerical calculation at special omega and special k. We fit it and we found this kind of form. So this for pure imaginary omega and k, we found the zeros for the denominator has this form, and the zero for numerator has this form. And we see that the post-gaping is a special point. If we recover to the Schwarzschild BTZ black hole coordinate, we see the post-gaping is exactly this one. We can also study the post-gaping from CFT. Again, for Masonist graviton case, for the energy momentum tensor, it's the same as the previous one. But for this new operator, which due to massive graviton, it's an operator with this conformal dimension. So here data is related to the deformation Chern-Simons coefficient. And we can get the retarded Green function to study the post-gaping, and we found the post-gaping again gives the same results from which we can we can get the same Lyapunov exponent and butterfly velocity as the previous results from OTOC. So both OTOC and post-gaping in the decommodification limit matches to each other in TMG case. Okay, let me summarize. So we have talked about OTOC and post-gaping for quantum chaos. They are both OTOC and post-gaping are 2 important signatures for quantum chaos. So we computed the quantum chaos for different systems. That is the rotating BTZ black hole for 3-dimensional Einstein gravity, rotating BTZ black hole for TMG, using these 2 methods, OTOC and post-gaping. We found that in the decommodification limit, they match quite well. However, for TMG case, in the decommodifications, and also this limit, mu is greater than 1 or mu equal to 1, these 2 methods match. Moreover, this mu, this regime, mu is bigger than 1 or equal to 1 is the limit that the chaos bound is saturated. The black hole is stable. The central charge of the dual CFT are positive or non-zero. So there are lots of open questions. I think the most interesting question is to study quantum chaos in other non-maximally chaotic systems using this OTOC and post-gaping to study their relations. That's the end of my talk. Thank you.
Okay, thank you, Jan. I have one question in your conclusion slides.
Okay.
Okay. Well, you probably already explained, but I missed. So here you emphasize there's a match in 2 methods in only high temperature limit.
Yeah.
Here, by 2 methods, you mean one is the pole skipping method
Yeah, yeah. And the other one is from OTOC.
Could
The
you
matching,
yeah, could you show me one example slide for that?
So for example,
uh.
for Einstein gravity, you should be very familiar. So from OTOC, I mean, for example, we get, this is what you get. So
yes, yes, yes.
And on Lyapunov exponents,
Yeah.
and butterfly velocities. This
Yes.
is what this is valid for the decommodification limit or high temperature limit. And from post-gaping, I mean, different post-gaping methods give the same result. So I just say post-gaping methods. And from post-gaping methods, we get the same chaotic parameters. I mean, either from dynamics or from holographic coordinator or from CFT.
But here I'm confusing because the beta is the arbitrary temperature.
Yeah, yeah.
So
but here we assume this phi is non-compact.
I see.
If it's periodic, there's some constraints until there's some like Fourier, so we should choose different bases.
Okay.
To your function.
Okay. I see. Okay. Thank you. And another question is, it seems that you want to constrain your system. You want to constrain the parameter of your system by requiring chaos bound.
Yeah, sure.
But how can you understand the relation? I mean, so if I choose some different parameter, then your gravity model will violate chaos bound. Then in that case, how can you understand that from the field theory point of view? For example, in your
yeah, that's a very interesting question, actually. So for example, for Einstein, so in the literature, people have computed Lyapunov exponent for Einstein Gauss-Bonnet gravity, for example.
Yeah.
So for Einstein Gauss-Bonnet gravity, there's a Gauss-Bonnet coefficient. Actually, we know there's some. So for example, if the Gauss-Bonnet coefficient is very large, then the dual theory is non-unitary, but there's no chaos bound for that situation.
I see.
So it seems that non-unitary or unitary has nothing to do with chaos bound. But and also for TMG case, if we study the Lyapunov exponents for shared BGZ black hole, but not for rotating BGZ black hole, we couldn't see any chaos bound violation. So it seems to me that the chaos bound violation is the relation between chaos bound violation and the unitary depends on the geometry or depends on the state of the dual field theory.
I see.
So I can only make this kind of statement.
Okay, thank you. So is there any question from audience? Any comment?
Sorry.
Yes.
I'm interested in the relation between conformal dimension and mu. And if mu is smaller than 1, so some chaos bound is broken.
Yeah.
I think VM is faster than speed of light.
Yeah.
So then is there relation between unitarity bound of mu and this? A unitarity bound of conformal dimension and mu?
So what we found, so first from CFT side, if mu is smaller than 1, so we have negative central charge. So which means the CFT in the regime mu is smaller than 1 will be non-unitary. This is what we have known from CFT, I mean ADS-CFT. On the other hand, from the computations on Lyapunov exponent, so if we compute the average of instantaneous Lyapunov exponent, we could say that when mu is smaller than 1, the average of instantaneous Lyapunov exponent could be larger than this 2 pi t, which violates the chaos bound. So in the case, I mean, mu smaller than 1, it seems that the non-unitary and chaos bound violation is the same, at least for rotating big Z black hole in TMG.
Okay. Thank you.
Thank you.
So any other question? Okay, so okay, if there is no more question, I would like to finish this session officially, but we can continue the discussion with the speaker. Okay, so let's thank Jan for his very interesting talk. Thank you.
Thank you.